Okay, I hope that you can now see the slide and also hear me. So, where we, what was the discussions? We are continuing that. We have discussed about the amplifiers. That the amplifier actually amplifies signal. Okay, so at the input you have an amplifier. Of the input side you have a small signal, and at the
অনেকজন
output
জয়েন
side.
হওয়ার চেষ্টা করছে, একটু জয়েনটা করিনি।
আচ্ছা। So you know that from the discussions previously that a small signal at the input of the amplifier, at the output you will get a large signal. That is the amplification. So amplifier does the amplification. That is, it actually boosts the signal at the output. The voltage and currents of the amplifier will be large, or in terms of AC power, it will boost the AC power. So that is the function of a particular amplifier. And last day we are discussing that this amplifier, whatever is the amplifier, in the middle you see the amplifier in the middle, you can see the triangular shape. That is the symbolization of the amplifier, and that triangle actually gives you what happened? Just a minute. Okay, so this triangle shape is the amplifier. You know that this is the amplifier in the middle. Just so this one. So this one is your amplifier. Okay. So this arrowhead, you see that there is a arrow is there. So signal actually propagates in this direction through the amplifier, and a small signal, that is a very small signal, at the output of the amplifier, you will get a very large signal. So this is the basic functions of the amplifier, and you have understood this one, that what is the function of amplifier. And also we have discussed how to build a amplifier circuit with the help of 3-terminal devices, just like the transistor. If you understand the circuit, whatever we have discussed previously, with the help of transistor, then you can build with other 3-terminal devices like FET, MOSFET. So what is the basic function? This is the basic. This much you can do with a particular amplifier, nothing more than that. Okay, so amplifier basically amplifies signal. At the input you have a small signal, and at the output you only get a larger signal. So that is specifically the function or the work of your amplifier, and you cannot do nothing with this amplifier except the amplification. So amplifier only amplifies the signal. Okay, so this amplifier only has this advantages, that it only amplifies the signal, but nothing it can do without the amplification. So it will only amplify the signal. But if we change slightly the constructions of the amplifier, that means if we change slightly something into the amplifier, like this one, suppose in this case, what we have seen in the last this class, that if we feedback the output, now we were changing the amplifiers, we are making some extra arrangement to the amplifier, and that extra arrangement is called the feedbacking. We have feedback, we have discussed last day, and that extra arrangement, though it is a very simple, You are not applying another amplifier, just you are applying another beta network, which is a passive network circuit. What is the function of the beta network we have discussed last day? That it will sample the output voltage or current here, and a fraction of that output voltage will feed back to this side. And that is, suppose here the voltage is feedback, so this is the feedback voltage. A fraction of the output voltage V0 is feedback by this beta network, and this is the feedback voltage VA. So VA by V0 is all equal to beta, which is always less than 1. This arrangement is a very simple one. You have connected a beta network, which is a passive network, and to sample to get some fraction of the output in the input side. Only this simple arrangement you have done with the amplifier, and the diversity of this system, electrical system, amplifier with the help of, together with the feedback, that is called the feedback amplifier. The diversity of this system is tremendous. Okay, one diversity we have seen, that is one capacity of this feedback amplifier. We have seen that it can generate signal itself. This is one of the very important aspects of the feedback amplifier. Positive, in case of positive feedback, if you make this loop gain A and beta, product of A beta equal to 1, then it can generate signal itself. We have calculated by very simple mathematics, and we have obtained to the conclusion that if you put A beta equal to 1, then this simple feedback amplifier can produce signal by itself, which is an oscillator. Not only that, this is one of the unique features of the positive feedback amplifier you can get from the feedbacking method, feedback arrangement. So this is one you can do. If you have a negative feedback, there are several other advantages you can obtain, which is not possible by any other means. Only you have to connect the amplifier together with a feedback network. If it is a negative feedback, then you can get several other advantages. Just like that, the stability of the circuit will be more. Okay, the noise will be reduced, distortion will be reduced, and several other advantages you can get. Lots of advantages are there if you have a negative feedback. And if you have a positive feedback, then you can generate. If you have a positive feedback, then we can generate signal. This system, positive feedback system, if you put A beta equal to 1, then it will generate signal. So we have discussed this thing last day. So this is the advantages of the feedback in this very simple beta network or the passive network feedback. If you connect with the amplifier, then you can get these facilities of the electronic circuits, which you cannot get by any other means. So that is why this feedback amplifier is very important. And lastly, we have discussed how the positive feedback, in case of positive feedback, we have obtained the gain expression. You have just remember the last day's class that this positive feedback gain is A by 1 minus A beta. If you put the A beta equal to 1, then the denominator becomes 0. So it gain becomes infinity. So from that, we have concluded that without any signal, you will get some signal at the output, finite amount of signal. That is the principle of the oscillator. And A beta equal to 1 is a Barkhausen criteria, where A may be complex, beta in general, A is complex quantity, beta is also complex quantity. And Barkhausen criteria says A beta equal to 1 is a complex equation. That means the magnitude of the gain should be 1. So this one. And the phase around the loop, so this is your loop, so phase around the loop, this loop, phase shift around the loop will be 0 degree or 360 degree or multiple of 360 degree is the phase shift should be. This is the oscillator conditions of the Barkhausen criteria to get some oscillation or the signal from a particular positive feedback amplifier circuit. So this we have discussed. Okay, I hope that you have understood the last day's class. Now I am asking you that, okay, there is, if you put, there is a positive feedback, and this positive feedback actually gives you, if you put A bit equal to 1, then you will get your signal here at the output, you will get your signal. So you will get a sinusoidal signal at the output without having any input. So this is the principle of the oscillator. So here you have 0 input. So there is no input applied. You have applied. You have no input applied, but you are still getting some output. Okay. So this is the oscillation or the oscillator. That means the circuit, positive feedback circuit, under the condition A beta equal to 1 will generate signal. So it will generate definitely a particular sinusoidal signal. Particular frequency of the signal will be generated at the output. So this is the oscillations. Signal is generated at the output, and just I have to draw the properly. So at this point, you are getting some signal. Okay, so this is your signal you are getting at the output side. That is the output of the oscillator. Now this signal is everlasting sinusoidal or cosine wave. It will continue with respect to time. So in this direction you have the time, that is the angle omega t or t, whatever be. This signal has a constant amplitude. It will have a amplitude of the signal will be constant. So this signal will have a constant amplitude, as well as the frequency of this signal. That you know the frequency. What is the meaning of the frequency? Frequency means you have to measure this one time period. So from this point to this point, you have one cycle. So this is your one cycle, and you have to measure the time period. That is the time horizontal axis. So you have to measure this time, and 1 by that time. This time is your t. Capital T is the time period. Okay, so capital T is your time period. So 1 by t is your frequency. So the output of the oscillator is a sinusoidal signal. It has two major parameters. One is the frequency, which is 1 by time period. If you call that frequency is omega 0 or f0, linear or circular. F0 is the linear, omega 0 is the circular. You know that omega 0 equal to 2 pi by t. Okay, so that is your omega 0. And the amplitude of this signal. So this is the amplitude A. So these two parameters is important for the output to define the output of this oscillator output, A and omega 0. So what will be the equation for the output? It may be A sine omega 0 t. So this is the output mathematical equation the oscillator at the output is generating. The frequency of the signal will be determined by this beta network, as I have just earlier classes, last day's class, I have discussed that the frequency, that how much will be the time period, that actually depends on the beta network. Okay, we will mathematical also prove, and you will understand, but for a particular oscillator circuit analysis, you will see that this beta network actually determines the frequency of the time period of the oscillation. The amplitude part, what will be the amplitude of the sine wave? So this is your amplitude of the sine wave. Now this amplitude part is a very difficult one, that how much will be the amplitude the oscillator circuit actually generates. This amplitude is beyond your syllabus. To how much amplitude is generated by the oscillator, this calculation is beyond your syllabus. Okay, we will only calculate omega 0, which is the frequency of the output signal. In the higher classes, you may have MTech class also. There is no scope to discuss this amplitude of the. Also, if you go into the research work or in a particular direction research work, then you will be able to know that this amplitude part, how to calculate this. This is a very difficult one, to calculate the amplitude of a particular oscillator output. Amplitude depends on this amplifier, and you have to find the nonlinear gain of the amplifier. Then you have to solve the differential equation. That differential equation is not easy to solve. If you solve it, then you will get what will be the actual amplitude of the. So we will discard that one. The amplitude part we will not discuss in this class. The frequency part, that means how much frequency will be generated by the signal, we will discuss. So as a whole, the output of this feedback amplifier, this is here is you have the output. It has a frequency part, has an amplitude part.
Someone trying to join him.
So we will only focus into the frequency part. We will discuss the amplitude part, but because the amplitude part is not in this class, in this course discussion, that requires a very long discussion, long differential equation solution. Actually, the Van der Pol equation you have to solve, and ultimately you have to find the equation. So that is a very difficult part. We will difficult means it is not so difficult, but that is beyond your syllabus. Okay. Now I am asking you a question that you have understood from these discussions that the positive feedback amplifier with the loop gain equal to 1 can generate some signal. So at the output of this feedback amplifier, when there is no input but still the circuit producing some output, so this is your output signal at the output of this positive feedback amplifier with the gain equal to 1. And also I have said that this frequency of this signal actually depends on the beta network. And the amplitude of the signal actually depends on the amplifier. Okay. So these two parameters of the output signal actually depends on the frequency of the signal is dependent on the beta network. Amplitude of the output signal actually depends on the amplifier. We will discuss this amplitude part. We will only focus into the frequency part, that means how much frequency actually generated by this amplifier circuit. Okay, can anybody say that you have not applied any input signal at the input side? So there is no input signal you have applied. Still the circuit actually generates the output signal. So there at the output side, you have a particular signal or particular frequency it will produce, it will generate. Can anybody say from where this signal actually appeared? There must be some source into this circuit, into this feedback arrangement, into this circuit amplifier and feedback arrangement. From that source, this signal actually appears. Can anybody say what is that source? Can anybody go guess this one? Have you understood my point? Have you got my point? Have you understood what I am asking?
Yes, sir.
Just guess that from there must be a source. The signal is actually appearing or coming from that source actually at the output. Do you know that what is that source? How the signal have been generated like this? Without having any input, you have not supplied any input AC signal. Within that circuit, somewhere there is that frequency signal is there, and that actually appears at the output. Can anybody guess? Can you guess that from where this signal actually appears? Have you understood? But what is the basic question that what I am asking actually? Everybody has got my point. Now just think that from where this actually comes from where this signal actually appears. So there must be some source from where this signal actually appearing at the output side. As you
Sir,
have not
input
applied.
VCC থেকে
Yeah, yeah.
স্যার ইনপুট ভিসিসি থেকে সিগন্যালটা গেইন করছে।
But input VCC is a constant signal. This is a AC signal, but input VCC, if you plot it, it is a constant signal. There is no sine wave. There is no sine signal is there in VCC. That is a flat constant 5 volt or 10 volt DC voltage. But it is a fluctuating AC signal. Okay, you have tried. Good. VCC may be a source. I am telling you, VCC, you have your guess. I cannot discard completely. But if the VCC is ideal, then it is not possible. But if the VCC is practical battery, then it is possible that from VCC there this signal may appear. Any other guess? Any other guess? Anyone try to get anything, any idea? Okay. Also, just I can say that this circuit, into this circuit, just as your friend said, into this system, you have only a constant DC power supply is there. So to energize the amplifier, because the beta network does not require any power supply because it is a passive network. Okay, so whatever is the output, a fraction of the output will be at the beta network feeding the input side, that is the feedback. So that is a passive network. It does not require any batteries or any energy supply, but the amplifier does require a battery DC supply. Why? Because the input of the amplifier is a small AC signal and output of the amplifier is a large AC signal. So amplifier has to feed some DC energy such that it can convert a part of that DC energy to the AC, and that is why the output is boosting. So we have discussed this thing, calculating efficiencies into the power amplifier. We have understood this thing. So there is no AC input is there. There is no AC input. Still, we are getting some at the output. We are getting some AC. This appears. So into this circuit, you have only a constant VCC, which is a DC power supply, and DC. This is if this VCC is ideal, then there is no AC part is there. Fluctuating current is no fluctuating current is there. Actually, this circuit contains some noise. Okay, so noise, you have noise, electrical noise is there. So amplifier circuit does contain some noise. Beta network does resistance, capacitance, whatever be, that has some electrical. Switch circuit, switch may produce some noise. If, as your friend said, if the VCC is not ideal, then there is maybe a fluctuation of the 10 volt supply. Very slight fluctuation, millivolt or microvolt order, but there may be, that is not constant. So there may be around the 10 volt, you have a slight fluctuation. That fluctuation is a noise. That noise actually may be anywhere in this circuit, in this electrical circuit, anywhere that fluctuating very small voltages, fluctuating voltages may be there. I don't know whether you have the idea of the electrical noise. It may vary. The current you have designed for the amplifier, suppose 1 milliampere current, but that current may not be constant. Usually it is not constant. It may fluctuate. Slight, very slight fluctuation may be there. You cannot make it ideally 1 milliampere. Okay, so number of electrons per second flow for 1 milliampere current to generate, it may not be same for every second. In some second, second, it may increase. It is in some second it may decrease. In this way, it can fluctuate. The number of electrons, you cannot guarantee that every second this much of electron will go. So there will be no fluctuation into the collector current 1 milliampere. That is not possible. So there may be a fluctuation in the collector current. There may be a fluctuation in the VCC voltage. Okay, there may be a fluctuation in the power supply line. There may be a fluctuation, that is the voltage drop across the resistance, that may also can fluctuate as the current flowing through the resistance slightly fluctuates, and the voltage across the resistance may also fluctuate. So voltage across the resistance which is fluctuating, it is called the thermal noise. Because of the random thermal motion of the electron, so there is noise in every part of this electrical circuit. And that noise is a very high, fluctuating current or voltages. And that noise contains all the frequencies from 0 to infinity. All the frequency components are present into that noise. So in every part of this circuit, you have an electrical noise, which is very small amount, maybe lower than the millivolt or milliampere current, maybe a microvolt order of noise is there. Very small fluctuation, voltage fluctuation or current fluctuation is everywhere into this circuit. When that noise signal, suppose here, we assume that to make you understand, we assume that this point you have a noise. That is a fluctuating voltage, the output, some noise is there. No signal have been generated. So this signal have not been generated. So erase these signals, okay? Only the circuit has noise. So noise means, suppose this point, okay, at the output of the amplifier, you have a DC voltage, suppose, and over this DC voltage, you have a fluctuating voltage. So this DC voltage is not constant. So there is a fluctuating, this DC voltage is fluctuating. It is not always constant. And that fluctuating part, if you divide this DC voltage, it has two parts. One is the constant DC voltage, and another is your fluctuating part. So that DC voltage is not exactly flat, constant. It is a noise is also there. So this is your noise. This noise signal, which is very small in magnitude, can be any part of the circuit, but we are assuming that this noise voltage is here. Here you have the noise voltage, suppose, for example. Then this noise voltage contains all frequencies from 0 frequency to infinity frequency, any frequency it can have. This is the nature of the noise. This noise signal, when it passes through this beta network, then it is filtered. Beta network is a frequency sensitive element network. That means it contains capacitors, resistors, and inductors. That capacitor and inductor is frequency sensitive element. Actually, this beta network is a band pass filter. It only selects a particular frequency. It only allows a particular frequency through this beta network. So among the noise, only a particular frequency, suppose omega 0 or f0, that will pass through this beta network. Okay, so the source is your noise. From the source, you have all the signals, all the frequencies are there, and this beta network only allow a particular signal. So at the output of the network, you have the noise signal, but a particular noise signal frequency. Okay, a particular noise frequency is there. That noise means the voltage. If you consider it as a voltage, noise voltage, then it is microvolt order, very low voltage. Okay, but it's still there, that microvolt order. But at the output of the beta network, now you have that noise magnitude voltage, but of a particular frequency. Okay, so this is the noise is the source of that signal, and beta network actually filters the particular frequency component from the noise, and that frequency component within this loop actually grow up, okay, and gives the signal at the output side. So this is the way by which the signal have been produced by this system. Have you understood this one? Have you understood this one?
Yes, sir.
Anybody has any doubt? Noise is everywhere, okay? You cannot eliminate noise from the nature. Everywhere. If you are talking about the sound noise, you have sound noise. If you considering the electrical noise, the electron motion is not just like the streamline constant motion. It is not like that. It is a thermal motion. Electrical motion is zigzag motion. it can randomly move in any direction. So that actually produces a noise in the current. So electrical, that is the steady current or constant current, that means the steady electron flow along a particular direction. If you applied a potential or the electric field, will not be always constant, because the electron motion is random thermal motion. But if you apply the electric field, the electron have a net resultant motion according to the electric field line, but it has that random motion. This random nature of the electrons of the charged particle produces noise in the electrical circuits. So that is the source of this oscillation. Only this system actually amplify a particular frequency noise at the output. Okay, so in this way, at the output of the oscillator, you get some signal without having any input. You have not applied any input, still you are getting some output from this oscillator. So this is the reason. We will now understand that how this noise signal actually can be generated at the output. We will now have a little bit discussion more what we are discussing. So we consider that there is a noise voltage or current, and there is a noise source is here. Assuming, and you have made this A, you know that oscillator to get the oscillation, you have the condition A beta equal to 1. Is not it? Just we have discussed from the mathematics that if you put positive feedback A beta equal to 1, at the output you can get oscillation. So let us now physically understand that how this oscillation is generated at the output of this system, which is just an amplifier and a positive feedback beta network is connected. No input is applied. So if you have a noise here, then that noise, as I have said, that the nature of this noise is a fluctuating voltage or current. So this is the voltage or current fluctuating, everlasting fluctuating voltages or current, very small in magnitude, which is of the microvolt order or microampere order, current fluctuation or voltage fluctuation. This noise contains all frequency components. When this noise signal at this point, suppose a particular noise, you consider a particular noise amplitude here, and when this noise signal actually travel through this beta network, suppose this noise signal travel through this beta network, and you have made this A and beta equal to 1. You have made this loop gain of this loop gain you have made 1. Then when the noise signal travels through the beta network and comes to this point, what will be the noise signal there? It will be reduced further, because the beta network actually at the output of the beta network you will get less than a fraction of the output you will get at the fraction of the signal here, whatever is the voltage here, you will get at the output of the beta network a fraction you will get. So noise signal at the output of the beta network will definitely have a less voltages. So noise signal again further be reduced, but when it travels through the beta network, this beta network eliminates all other frequencies except a particular frequency, which is omega 0. So at this point now, you are getting a very small microvolt order of signal here. Again, the initial noise is N of t, and the output of the beta network is less than that N of t, but it only has only single frequency is there. When this noise signal at the output of the beta, when it passes through the amplifier A, amplifier function is just to amplify the signal. Okay, so at this point, how much you will get, how much noise signal you will get? You will get a particular frequency, omega 0 frequency noise signal here, but you will get the same voltage again, but the filtered noise voltage, that means all frequency have been discarded, only a particular frequency you will get here, but you will get the same magnitude. Why? Because when the signal travel through the beta network, it will be multiplied by beta. When the signal travel through the amplifier A, it will be multiplied by A beta A. So A into beta equal to 1, you have put the A beta equal to 1. So when the noise signal at the output travel through this loop, it will only multiplied by 1. That is A beta equal to 1. So it will not amplify at the output of this signal. At the output of this here, you have started from this point and traveled through this loop. The noise is traveled through this loop and comes here again. Then it will be multiplied by beta first in this path, then through the amplifier A first. So beta first, then A, it will be multiplied by A, but A beta equal to as A beta equal to 1. So at this point, again, you will get the same magnitude noise, but there will be some little bit of filtering will be there. This beta network will filter the noise signal for a particular frequency. So you will get here some particular frequency noise signal you will get. It is not a complete signal you will get. So at the output, you will again get a noise signal. If you put the A beta equal to 1. So if you put initially, if you put A beta equal to 1, oscillator, you get nothing. You will not get any signal. You cannot see any signal at the output of the. If you connect a CRO and put initially that A beta equal to 1, you never will get the signal. You will not get the oscillator output if you put initially A beta equal to 1. What you have to do, you have to put A beta slightly greater than 1 initially to start the oscillation. So initially what happens, this loop, what is the gain of this loop? When the signal noise signal passes through the beta, it will be multiplied by beta. When the signal travels through the amplifier A, it will be multiplied by the gain of the amplifier. If you put A beta equal to 1, so at this position for one round trip journey of the noise signal, it will get the same magnitude there. For one loop journey, the noise signal will have the same value. It will not be amplified, but it will be filtered. A particular frequency signal, noise signal will be there, but the magnitude will be same. So for this reason, initially, if you put A into beta equal to 1, you will not get any signal at the output of the oscillator. What you have to do, that is called the starting oscillation. So initially, you have to make this A beta slightly greater than 1. Okay. So initially, you have to make this A beta slightly greater than 1. That means if you put A into beta slightly greater than 1, then what happens? If the noise signal from this point travels through this loop and comes to this position, then it will be multiplied by A into beta, and that A beta is greater than 1. So here now, for fast loop journey, the noise signal appearing here will be larger than the initial noise signal. Then that noise signal again travels another loop, and the second time when it travels and reach the output, it will be much higher than the previous noise voltages. In this way, it actually repeatedly loops around, circulates around this loop, A beta loop, which is greater than 1. So that noise signal, every loop traversal of the loop at the output side, it will grow. And in this way, the noise signal will get a very high voltage. And that is the growing of the signal at the output of this amplifier, of this loop, if you put A into beta slightly greater than 1. Okay. So in this way, the signal actually grow. So noise signal, when one loop have been covered by this noise signal, one loop have been traveled by this noise signal, A beta is slightly greater than 1. Then you can see that here you will just see so initially this point is the noise level, which is close to 0. One traversal of the loop, the signal is growing. You see that the signal have now increased. And as the noise is looping here, after several loops, the signal will grow. And in this way, that noise signal at the output actually growing. You just see that signal is growing. As it travels the loop further and further, it actually grow up because A into beta is greater than 1. So each loop, it will grow slightly. After the traversal of each loop, it will grow slightly from the previous value. Next loop, it will grow again. So in this way, the signal actually grow up from the noise level to a high value. The only thing you have to consider that this beta network only filters the noise. Noise contains all the frequency components, but the beta network will allow only a particular frequency. So the noise signal traversing the loop repeatedly, and the beta network actually filtering also for a particular frequency. That is why the signal actually grow, and a particular frequency signal actually grow at the output of this oscillator. So in this way, you are getting your desired omega 0 frequency or particular frequency signal that is actually growing at the output of this oscillator. So this is how the oscillator actually starts up. So at this point now, you have this signal is actually growing from the noise level to the large value, and a particular frequency, you see that this is frequency of this signal is constant. So the time period of the signal is constant because this is the time period, it is constant, and a particular frequency will be grow up because of the beta network, because the beta network only allows a particular frequency from the noise. So that particular noise frequency will grow up in this loop if you put initially a beta greater than 1. So in this way, the signal actually grow up. But when the signal reaches a maximum value, when the signal reaches to a very high value, so this is suppose the high value, at the high value signal, this amplifier will become a nonlinear one. If the signal at the input of the amplifier is very high, it will actually restrict the signal growing. The nonlinearity of the amplifier will cut the signal growing. It will not allow further increase of the signal. So that is why after a certain point you are getting a constant signal, because the amplifier nonlinearity actually restrict the signal up to that level. It will not further allow the increase of the signal. It will restrict the signal and cut out the amplitude of the signal, growing signal, and it will make them constant. So in this way, the noise signal actually produces at the output a oscillation signal. Have you understood this one? Is there any confusion? Anybody ask anything? Anybody has any doubt? You just see here that when the signal grows from the noise level to the high value, during that period, a initial closed loop gain should be greater than 1. So initially you have to put a beta greater than 1. Then the noise signal can grow. If every loop traveling through the loop, it will be multiplied by a greater than 1 number. So repeatedly it will loop into the circulate into that loop, and it will grow up. So this is the growing of the signal from the noise level to a high value. If you put this a loop gain, closed loop gain, a beta, this is a ACL, that means the closed loop gain, that means a beta equal to slightly greater than 1. When the signal has grown enough, the amplitude of the signal is very high, then of the amplifier is a semiconductor device. You have made an amplifier, suppose with the help of a transistor. The transistor is a semiconductor device, and that semiconductor device has a nonlinearity. If the signal grows too fast, it will ultimately, after a certain voltage, it will cut out the signal because of the nonlinearity, and that amplifier will restrict the signal to a particular constant value. It will not allow any further signal growth. And at that point, when the amplifier nonlinearity makes the signal constant, then automatically the gain of this amplifier, becomes lowered. Automatically the gain falls. And when the signal grows up too much, the gain of the amplifier falls down, and in such a manner that your A beta becomes equal to 1. So automatically this initial setup is A beta gets slightly greater than 1 will automatically becomes equal to 1 when the sustained oscillation or the constant oscillation is producing by the oscillator. The gain of the amplifier will automatically fall to make this ACL equal to 1. So amplifier gain slightly falls down to make this closed loop gain equal to 1. Then if the signal travels through the loop, it cannot grow because the A beta has become 1 automatically. Because semiconductor device, amplifier semiconductor device is a semiconductor device. So it will automatically restrict the amplitude and the gain will fall. It will automatically make the A beta equal to 1. So after that, the signal will not grow. So in this way, the signal actually grow up in a particular oscillator circuit. So the noise is the source, and from the noise, a particular frequency signal actually grow at the output. But to start the oscillator, you have to initially put this A beta slightly greater than 1. And then automatically the circuit will make A beta equal to 1 when the signal has grown enough. And when the oscillator is producing sustained oscillation, the closed loop gain will automatically reset it to the A beta equal to 1. So in this way, the signal actually generates within an oscillator system at the output of the oscillator circuit. So that is why you see these sentences. It is written here that startup condition. This is called the startup condition. So to start the oscillator, you have to put the A beta slightly greater than 1 initially. If you don't put the A beta slightly greater than 1, if you design the oscillator for A beta equal to 1 initially, then you never will get the signal at the output of the oscillator. So initially you have to set A beta slightly greater than 1. Oscillator signal will grow, noise will grow up in the output side, a particular frequency, and automatically the amplifier gain will be lowered and A beta will become 1, and you will get a constant sustained oscillation at the output of the oscillator. The signal generates from the noise signal. Okay. When it passes through the beta network, it only allows a particular frequency omega 0. Being the oscillation frequency, initially the loop gain A beta is slightly greater than 1, causes the signal to grow within this loop. Within this loop, initially you have to set the A beta slightly greater than 1. That noise signal, each traversal of the loop will grow up at this point. When the signal builds up to a desired level, the amplifier gain A then decreases, falls down due to the nonlinearity, such that the loop gain A beta becomes equal to 1 for sustained oscillation. So in this way, the oscillation actually develops within the oscillator circuit, and in the sustained oscillation condition, automatically the gain A beta becomes equal to 1. So that Barkhausen criteria we have get from the mathematical analysis that actually tells you the condition at the sustained oscillation. When the signal is sustained, that means the constant signal you are getting at the output. That analysis we have done previously, that is for this region. That is why we have obtained A beta equal to 1. to produce or to sustain a oscillation at the output of this positive feedback loop, you have to make A beta equal to 1. That is the sustained oscillation condition. But to start from the noise level, initially you have to put this to grow the signal. Initially you have to put the closed loop gain A beta slightly greater than 1 at the starting of the oscillator. So at the starting of the oscillator, you have the closed loop gain slightly greater than 1. So this is called the startup of the oscillator. If you don't do that, if you don't design the oscillator for A beta slightly greater than 1, oscillator will never start up. When the oscillator, if you put A beta slightly greater than 1, oscillator will start up, and in the sustained oscillation condition, it will automatically set itself A beta equal to 1 and produce the everlasting constant signal as long as you put the power supply VCC to that circuit. Is there any question? Is anyone has any doubt? Any question is there? Have you understood this one? If you have understood this one, then also respond such that I can realize that you have got it.
Yes, sir.
Any doubt? Any doubt for anybody? And last day, one of your friend is asking, saying that, sir, we have seen the growing signal in the CRO. So in this way, from the noise level, you will get this signal. This picture you can see actually from the at the DSO, that this growing signal, and ultimately it becomes constant. You can obtain from, you can get for a practical oscillator circuit. If you see in the DSO, digital storage oscilloscope, this you can see the startup of the oscillator. Okay. So if you have understood, yeah.
We have another class after this.
When?
It's 10, 11, 15.
11:40 মনে হয়। 11:40. Your friend is too early for the next class. Okay. ও হয়তো রুটিনটা একটু মিস করেছে। তুমি দেখো রুটিনটা দেখো, এটা 10:40 বা 11:40 হবে, 11:40 হবে। তোমাদের যে শুক্রবার দিন মনে হয় তোমাদের 10:50 বা 11টা থেকে আছে মনে হয়। তুমি বুঝতে পেরেছো যে বলছো যে আরেকটা ক্লাস আছে, বুঝেছো ব্যাপারটা?
হ্যাঁ স্যার, আমাদের অফলাইনে আছে স্যার ল্যাব।
ও, অফলাইনে ল্যাব আছে। ও, তোমাদেরকে যেতে হবে ফিজিক্যালি?
হ্যাঁ স্যার।
কি করবে তাহলে?
আমরা যাচ্ছি।
ও, তা কি করবে তাহলে? তোমরা কি সবাই ওরকম ভাবে যাচ্ছ ইউনিভার্সিটি অফলাইন ল্যাব করার জন্য? আচ্ছা 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 আচ্ছা। বাকি বাকি যারা আছে তারা বুঝতে পেরেছো? বুঝেছো তোমরা না? কোনো কোশ্চেন আছে কি?
হ্যাঁ স্যার, ক্লিয়ার হয়েছে স্যার। আরো কিছুটা
Clear?
ডাউট হলে স্যার পরে নিয়ে আবার
আচ্ছা, ইউ আর,
টপিকটা ডাউট আছে তখন জিজ্ঞেস করবো স্যার।
ও আচ্ছা, ঠিক আছে। তাহলে আমি কি করব, কন্টিনিউ করব? কারণ আমাকে তো সিলেবাসটা কিছুটা শেষ করতে হবে, বেশ কিছুটা শেষ করতে হবে, ঠিক আছে? বাকি যারা আছো তারা তারা কি বলছে, মানে আর ইউ গেটিং মি?
স্যার আপনি কন্টিনিউ করুন।
আচ্ছা ঠিক আছে। দেখো, now we take a particular example of a oscillator, then it will be very clear to you that what is actually happening, how this actually happening, how to calculate the frequency of oscillation, and how to understand the oscillation condition. We need a particular oscillator circuit. So we will now design, this block, which is the positive feedback block for A beta equal to 1. This block will be converted into an electrical circuit. We will now discuss a particular electrical circuit, the oscillator circuit, and we will choose initially the wine bridge oscillator circuit, which is a very popular circuit, oscillator circuit, and we will use that circuit to understand that how to calculate the frequency and how to this amplifier section, how this amplifier section is there, and how this beta network section is there connected into the circuit. We will try to understand this A beta, this loop circuit in a particular oscillator, which is called the wine bridge oscillator circuit. So this is a wine bridge oscillator circuit. As in the figure, you can see that this is a wine bridge oscillator circuit. Wine bridge, you can understand this. Wine actually is the name of the scientist, and the bridge actually responsible for. Are you familiar with the Wheatstone bridge? You have learned in the high secondary class. Shovik, Wheatstone bridge, you have you have idea. In the electrical class, have you Anderson bridge or the other type of bridge? Have you learned this one? না, তোমাদের যে ইলেকট্রিক্যাল সার্কিট গুলো আছে সেখানে এসি অ্যানালিসিসে পাওনি অ্যান্ডারসন ব্রিজ বা ওই জাতীয় ব্রিজ পাওনি? ওই একই টাইপের, সবই ওই পিকিউআরএস। ওখানে শুধু ইন্ডাক্টর ক্যাপাসিটার, ইন্ডাক্টর মেনলি থাকে, ইন্ডাক্টর ক্যাপাসিটার অ্যান্ডারসন ব্রিজে বা এতে। যাই হোক, this is the bridge actually. This is a wine bridge oscillator circuit. Okay, this circuit is drawn here like this one. This circuit is drawn here like this one. Okay, but it can be, you can draw the same circuit with the bridge formation. If you do that, then this circuit will be look like this one. So this is the bridge. The same circuit you can see, if you want to understand the bridge. So this is your bridge actually. The entire circuit can also be drawn in the bridge fashion. So this may be the P, this may be Q, this may be R, this may be S. So that is the Wheatstone bridge, the PQRS format. That is also you can draw the circuit in a bridge fashion. That is why it is also popularly known as a bridge. So that is why it is called the wine bridge oscillator. Okay, so the construction of the circuit is like this. You see that I just has to. So are you familiar with this triangular shape? What is this triangular shape? Are you familiar with this one? Yeah.
Op amp.
Yeah, very good. This is a op amp. This is it is a looks like the symbol of an amplifier, but within the this triangular shape, you see that this is a minus and this is plus is there for the two input. So one is the inverting input and second is the non-inverting input. So it definitely is a op amp. So this is a op amp operational amplifier you have learned in the earlier classes. Now, can you say that I am saying that the just now you see that, so this op amp, this is the this is the non-inverting input terminal. Okay, I just has to enlarge this figure. So this is the maximum. Okay, so this is the non-inverting inverting input terminal, and this is the non-inverting input terminal of the op amp. Now you see that inverting input terminal has a resistance R1 connected, and the other end of the resistance is connected to the ground. And between the inverting input terminal and the output terminal, you have a feedback resistance R2. And non-inverting input terminal is actually, it is connected to a particular voltage which is VA. So voltage is connected to the non-inverting input terminal. Voltage is connected here because this is the voltage is applied here. I am just identifying the amplifier here. The op-amp is a semiconductor device. Okay, it is an amplifier, but there is an amplifier in this circuit. First, you have to understand the amplifier A, then you have to understand the beta network and the connection, then you can analyze the circuit. So first, I am identifying the amplifier in this circuit. So this op-amp, the non-inverting input terminal, is connected to a source which is VA. So this is the voltage applied to this non-inverting input terminal. So there is a voltage source here. You can think of like this. So there is a voltage source here connected to the non-inverting input terminal, and the inverting input terminal, at the input side you have a resistance R1 between ground and the inverting input terminal, and R2 resistance is connected between the inverting input terminal and the output. Can anybody recognize the amplifier with what is the type of this op-amp amplifier is connected here? Can anyone guess this amplifier? So amplifier is this section. So this is the amplifier section. Amplifier, this section is built with the op-amp. This is the input to the non-inverting input terminal, and R1, R2 is connected at the inverting input terminal. Can you identify? Can anyone identify the op-amp amplifier here? Which op-amp amplifier is connected here? Anybody? Anyone?
Sir, cascading of op-amp.
ক্যাসকেডিং অপ অ্যাম্প বলে কোনো অ্যাম্পলিফায়ার তো শুনিনি আমি, তো যেটা শুনেছি সেটা জানি, সেটা হচ্ছে ইনভার্টিং, নন ইনভার্টিং,
হ্যাঁ,
সামার, তারপরে ধরো ডিফারেন্সিয়াল অ্যাম্পলিফায়ার, ইন্টিগ্রেটর, ডিফারেন্সিয়েটর। এইটা হচ্ছে, এটা বলো ইনভার্টিং অ্যাম্পলিফায়ার না নন ইনভার্টিং অ্যাম্পলিফায়ার? ইনপুটটা কোথায় কানেক্টেড আছে? এই যে ইনপুটটা কানেক্টেড আছে কোথায়? ভিএ ইনপুটটা কানেক্টেড আছে তো নন ইনভার্টিং ইনপুট টার্মিনালে কানেক্টেড আছে, তাই তো?
হ্যাঁ স্যার।
তাই তো। আর R1 রেজিস্ট্যান্সটা গ্রাউন্ডে কানেক্টেড আছে, তাহলে এটা কোন কি অ্যাম্পলিফায়ার? অপ অ্যাম্পের নন ইনভার্টিং ইনপুট অ্যাম্পলিফায়ার। অপ অ্যাম্পের দুটো অ্যাম্পলিফায়ার, ইনিশিয়াল যেটা হচ্ছে ইনভার্টিং অ্যাম্পলিফায়ার, নন ইনভার্টিং অ্যাম্পলিফায়ার, তাই তো? এটা হচ্ছে নন ইনভার্টিং অ্যাম্পলিফায়ার। ভুলে গেছো মনে হয় অপ অ্যাম্পের সমস্ত। বুঝতে পারছো? হ্যালো,
হ্যাঁ স্যার, বুঝতে পারছি।
এটা কোন অ্যাম্পলিফায়ার? এটা হচ্ছে নন ইনভার্টিং ইনপুট অ্যাম্পলিফায়ার অফ দ্য অপ অ্যাম্প। তুমি যদি ইনপুটটা যদি এই R1 এর এখানে থাকতো, ইনপুটটা যদি এখানে থাকতো, এইখানে যদি ইনপুটটা কানেক্টেড থাকতো, আর এই পয়েন্টটা যদি গ্রাউন্ডে থাকতো, তাহলে দেখো ইনপুটটা ইজ কানেক্টেড টু দ্য ইনভার্টিং ইনপুট টার্মিনাল, দ্যাট উইল বিকাম এ ইনভার্টিং ইনপুট টার্মিনাল, inverting input amplifier, op amp amplifier. What will be the gain? Gain will be minus R2 by R1. But in this case, you have a non-inverting input amplifier. Okay? এখানে কি আছে? Non-inverting input amplifier আছে, যেখানে ইনপুটটা is connected to this point, and R1 is connected to ground, and R2 is connected in the feedback path. So this is a non-inverting input amplifier, and gain will be 1 plus R2 by R1. What will be the gain of this amplifier? This is entire thing is an amplifier which is constructed with the op amp, and that is the non-inverting input amplifier, and the gain of this amplifier is 1 plus R2 by R1. So this is the gain of the amplifier. So this is the amplifier section in this circuit. Okay, so this gain of the amplifier, this is the amplifier section in this A beta network. So this is the amplifier. This amplifier has a gain, this one, A equal to 1 plus R2 by R1. So this is the gain of this amplifier, A equal to 1 plus R2 by R1. Another network is connected between the output and the input side. So this is your input side and this is your output side. You see that this network is connected between input side and the output side. This network actually tapping the output voltage V0 and producing a fraction of the output voltage here at the input side. Okay, so that is the that is your feedback voltage, and that is again connected to the input of the amplifier. That feedback voltage is equal to the input of the amplifier, because we have seen that whatever is the feedback voltage in the oscillator system, that is also connected to the input side. So that is the output voltage. A fraction of the output voltage is generated by this network, which is the beta network. So this is your beta network. Okay, so this is your beta network, and this is your amplifier A. So this beta network is tapping the output voltage V0 and producing a feedback voltage here at this point, and that is your VA, and that is actually connected to the input of the amplifier A. So this is the A. In the top you have the A, just I have written there. In the top you have A, and in the bottom in the bottom you have the beta. So this is your A beta network. Now you see that how the beta network is connected. What is the construction of this beta network? I have said that the beta network is a passive network. So for this reason, just take a close look to the beta network. Just see the beta network here. So this is the output of the amplifier, and remember the feedback amplifier, that output of the amplifier is connected, beta network is connected to the output of the amplifier. So this beta network here is connected here at the output of the amplifier. The beta network is like this. So this is a series combination of the CR circuit, and this is a parallel combination of the CR circuit between ground and this point, non-inverting input terminal. You have a parallel combination of the CR circuit, and between the output and the non-inverting input terminal you have a series combination of the CR circuit. So this is the construction of the beta network. So it is, you just see that the beta network, which is this one, only have capacitor and resistor. So this beta network only have the capacitor and resistor. I have said that the beta network is a passive network. And now within this network, you take a close look, you don't have any amplifier. Only you have passive circuit elements like resistance and capacitance. Okay, and this beta network is connected at this point, which is the output of the amplifier, and at this point, which is the input of the amplifier. So that is the beta network, and this is the construction of the beta network, and that part of the circuit is the beta network. So upper part of the circuit is the gain of the amplifier, gain A, amplifier A. Upper part of the circuit, you just identify the two sections, A, beta. So this part is your amplifier A. So this is your A, and the rest of the part, that is this part, this is your beta network, which is connected between output and the input of the amplifier. So this is your beta network. Okay, so in this way, the A beta, you can identify the A beta in this circuit, which is the wine bridge oscillator circuit. And the beta network is a passive network. It is the series combination of CR connected between the output voltage, output of the amplifier, and the non-inverting input terminal, and a parallel combination of CR circuit, which is connected between the non-inverting input terminal, plus terminal of the op amp, and the ground. So this is your construction of the beta network. Now we will analyze this circuit, and we will calculate the frequency of this oscillation. So what is the oscillation is actually producing by this circuit. So in order to do that, we just analyze the beta network first. So we have to analyze the beta network first, that what is the beta network actually doing here. So we divide this beta network in two parts to reduce the complexity of analysis. We divide this beta network in two impedances. We think that this CR, series CR, we can consider this as a section which is the series of the CR, capacitor and resistance, and call it as ZS, which is the series combination of capacitance and resistance. Okay, are you getting? I hope so. That this is the series combination of the capacitance and resistance. We call it as a single impedance, which is ZS. And this parallel combination of CR, which is connected between the non-inverting input terminal, plus terminal of the op-amp and the ground, this parallel combination of CR, we consider it as a impedance, which is the parallel combination of C and R, which is a single impedance we considering, that is your ZP. So as if here between this point and this point, you have a one impedance is connected, which is ZS, and between this point and ground, you have another impedance is connected, which is ZP. So this is the construction of the beta network. We are assuming some single impedances to reduces the calculation. That will easily calculate the circuit beta fraction. Okay. So ZS is the combination of CR, and ZP is the combination that is the equivalent impedance of the C and R parallel. Now let us very quickly calculate this ZS and ZP, because it is very easy. You are from the electrical branch, you can do it better than me. What is ZS? Now we calculate ZS. So what will be the ZS? ZS is the series combinations of the C and R. What will be the series combination of the CR? What is the impedance of the capacitor? 1 by SC, where S equal to J omega. So impedance ZS is resistance R plus the impedance of the capacitor, which is 1 by SC, where S equal to J omega. You know this thing, okay? I don't need to repeat this one because already you know this thing from the circuit theory classes. So ZS is R plus 1 by SC. So this is your ZS, where S equal to 1 by J omega C, 1 by J omega C, 1 by J omega, sorry, S equal to J omega. Now let us calculate similarly the ZP. What will be the ZP, impedance ZP, which is the equivalent impedance of the parallel combination of resistance and capacitance. How to calculate the parallel combination equivalent impedance? You know that if you have two resistances R1, R2 connected in parallel, the equivalent resistance will be R1, R2 by R1 plus R2. So that is the formula. So you apply this formula in this case in terms of impedance. What will be, how to calculate, get the expressions for ZP? So this is your ZP. It is a parallel combination of the resistance R and the parallel combinations of capacitor impedance C. Impedance of the capacitor C. So it is R into impedance of the capacitor. It is R into 1 by SC, which is the impedance of the capacitor, parallel combination formula. In the denominator, you have R plus impedance of the capacitor. So multiplication of the capacitor impedances, resistances or impedances in the numerator, and summation of the resistances or impedances in the denominator. So this is the formula for the parallel combination to calculate the impedance for the parallel combination. So ZP should be equal to R into SC divided by R plus 1 by SC. R into 1 by SC divided by R plus 1 by SC. So this is the formula, this is the expression for ZP. If you simplify this, so it will get this one. If you rationalize the denominator and numerator, that means you have to multiply the numerator by SC and denominator by SC, then you will get this R by 1 plus SCR. Is there any difficulty to understand this ZP and ZS? Have you understood this one? Any other, anyone has any doubt? This is a very simple circuit theory application. Anyone has any other doubt? Now you see, I hope that there is no doubt. So now we have to calculate beta. Beta is VF by V0, which VF is the feedback voltage and V0 is the output voltage. So beta network is connected between the output and the feedback point. So at the feedback point, you have the VF, and at the output point, you have the V0. So beta fraction, beta is equal to VF by V0. Here in this case, this is your beta network. This is the V0 point, and this point is feedback to the amplifier, and that feedback voltage is the input voltage. So VA is the feedback voltage or input voltage of the amplifier. Then what is the fraction beta? Then beta fraction will be the feedback voltage, that is VA, divided by the output voltage V0. So beta should be VA by V0. Now how to calculate this VA by V0? You have to calculate this VA by V0. If you can calculate this one, then it is very easy to analyze the rest of the circuit. That we have to find the potential at this point, which is a fraction of the output voltage. So we have to consider the current into this picture. So from the output point, a current is flowing through this electrical path, that means through this series ZS path, and again to the parallel ZP path to the ground. So this current is flowing in this way. Some current is flowing in this way. When this current flow through this parallel RC combination, that means through this ZP, it will produce a voltage here with respect to this ground, and that is your output voltage VA. So there is no other way the current can go. You can think that the current may go in this direction, but the op-amp, you know that the op-amp input impedance is infinite. This is the ideal characteristics of the op-amp. It does not allow any current to the input side of the op-amp. So in this direction, if the current try to flow, it will face the infinite input impedance of the open circuit. So current cannot flow in this direction. So in this direction, no current actually flowing. So current actually only flowing along the path which have been shown. Then what will be the potential VA? What will be the ratio of this VA? Can anybody say? If suppose the magnitude of the current, is I. I need some response that such that I can understand that you are getting my point. So this is the magnitude of the current.
sir.
That is actually, this is the magnitude of the current that is flowing in this way. It is flowing through ZS, then through ZP, as if it is flowing through the series of ZS and ZP, because no current can flow inside the op-amp. So no current can flow here. So current is actually flowing in this direction, through ZS, then through ZP to the ground. Then what will be the current? Current I should be V0 divided by ZS plus ZP. That is the current. And what will be VA? The voltage developed across ZP. It will be multiplied, current multiplied by ZP, the parallel combination of resistance ZP. So VA should be the current I divided, current I multiplied by ZP. And what is current? Current equal to V0 by ZS plus ZP. So what is the ratio of VA feedback voltage by the output voltage? It should be ZP by ZS plus ZP. If you analyze like this, then you will get the beta fraction of the voltage generated by this beta network, which is the feedback voltage. That beta should be VA by V0. And you know that VA equal to ZP into current, and by V0 means what is V0? ZS plus ZP into current. So current in the numerator and denominator cancels out, and you will get this expression ZP by ZS plus ZP. So that will be your equation for the to calculate that is the equation to calculate the beta. So what is the feedback factor beta? Beta is nothing but feedback voltage VA divided by V0, and in this analysis, taking a current, we can calculate this VA by V0 ratio, and just I have shown that how to calculate. So you will obtain this one, ZP by ZS plus ZP. So this is your beta. What is the feedback factor beta of this beta network? It is ZS by ZS plus ZP. And what is ZS ZP? We have calculated earlier. Also, we have an amplifier, and we have seen that this is the amplifier section. It is a non-inverting amplifier with the help of op amp, and that amplifier gain A. So this is the gain of the amplifier. We know this amplifier gain. We have learned in the basic electronics class. It is 1 plus R2 by R1. So we have the gain expression A. We have the beta expression ZP by ZS plus ZP. Then what will be the condition of the oscillation? A into beta should be equal to 1. So we now multiply A beta expression and equate to the 1. That is the sustained oscillation condition, and we will get some expression from that. So just very quickly apply this one here. Now it is just the mathematics, okay? So for the sustained oscillation condition, you have A beta equal to 1. So now you have to put the value of A equal to 1 plus R2 by R1. So A equal to just 1 plus R2 by R1. What is beta? Beta is this one. This one ZP by ZS plus ZP. So beta equal to ZP by ZS plus ZP. It is equal to 1. Then do some mathematics. You you put this ZP by ZS plus ZP in the right hand side of this equation. If you do that, then it will become 1 plus ZS by ZP. Is that okay? It is not very difficult one. So this one cancels out, and ultimately it will give you this one. So it is ZS by ZP equal to R2 by R1. Have you got it? It's a very easy one. Okay. Then we have to now put ZS and ZP. So what is your ZS? You see here ZS equal to this one, R plus 1 by SC. So ZS equal to, you put ZS. So this is your ZS, R plus 1 by SC, divided by ZP. What is ZP? Parallel combination of resistor and capacitor. It is R by 1 plus SCR. So you put here 1 by ZP equal to 1 plus SCR by R equal to R2 by R1. So this is in that equation. Okay. So we come to this equation. Then, so you just remember this equation, this one. R plus 1 by SC into 1 plus SCR by R equal to R2 by R1. From this equation, we get this one. So, sorry, from this equation, just this is just mathematics, so it is, don't be so don't worry this one. So from this equation, the first line you see that R plus 1 by SC. So what was that? R plus 1 by SC into 1 plus SCR. That means 1 by R plus SC. So that is have been done here. So R plus 1 by SC into 1 by R plus SC equal to your R2 by R1. Okay, can you understand that? This is R plus SC remains same. You divide this R. So 1 by R plus SCR by R, that means SC equal to R2 by R1. So you will get this one. So this one, so R plus 1 by SC into 1 by R plus SC equal to R2 by R1. So this is you have got from that equation. The second equation you see, now rationalize the left hand side. So if you multiply these two brackets, R plus 1 by SC, 1 by R plus SC, then what will be the outcome? So this you will get 1 plus SCR plus 1 by SCR plus 1. Have you got this one? First, you have to multiply this one with the help of this. I cannot point here, but okay. First, this R and 1 by R, multiply these two, then you will get this one. Then R into SC, SCR, then 1 by SC into 1 by R, 1 by SCR, 1 by SC into 1 SC equal to plus 1 equal to R2 by R1. So this you have got. Then Now this S is a complex quantity. S means J into omega. Now substitute S equal to J omega. So you will get this one, and this one will put you 2, and this S equal to J omega, take the J common. Then it will be S equal to J omega, so omega CR. So this will give you omega CR, and this will give you minus 1 by omega CR, because S in equal to J omega in the denominator. If you put the J in the numerator, it will become minus, so 1 by omega CR equal to R2 by R1. Now this equation, what we have got here, this equation, you see the equation. This equation we have got putting A beta equal to 1, where we have calculated the gain of the amplifier A in circuit parameters, and also we have calculated the feedback factor beta by analyzing the beta network circuit. And substituting A beta equal to 1, we have got this equation. Now this equation is a complex equation on the left hand side. And the right hand side, you have a real quantity R2 by R1. Resistance cannot be complex. Okay, you know that resistance is a real circuit element. The real value will be there, but the capacitor is always a complex J omega. The J part is there. So resistance is a real part. So the right hand side of this equation is a real quantity, but the left hand side equation, you have the real part 2 and the imaginary part. This is the imaginary part, J into omega CR minus 1 by omega CR. So you have to solve this equation. You can understand easily that this equation should be equated. The real part should be equated on the both sides of the equation. If you do that, then R2 by R1 should be equal to 2. So that is equating the real part. You got R2 by R1 equal to 2, or R2 should be equal to twice R1. And the imaginary part, J part, that is omega CR minus 1 by omega CR, should be equal to 0, because there is no complex, or you can say that it is plus J part into 0 is there. So this part is equal to 0. So for equating that one, you will get the imaginary part. Equating the imaginary part to the 0, you can get this one. So this is the equating the imaginary part to 0. So you are getting this one. From this equation, you can get the oscillation frequency, because this expression, you see that the frequency omega is present. So that is the oscillation frequency, or the how much the frequency is generated by the oscillator circuit, wine bridge oscillator circuit, that is present into this. So omega 0 should be equal to 1 by CR, or F0 equal to linear frequency will be 1 by 2 pi CR. So this is the way you can calculate the frequency of oscillation at the output of the wine bridge oscillator by analyzing the circuit, calculating the gain of the amplifier, calculating the beta of the beta network, and putting that A beta equal to 1. You can get the this frequency of the oscillation. So this is the frequency of the oscillations. Omega 0 equal to 1 by CR, and F0 equal to 1 by SCR. Now check this frequency. Frequency depends on 1 by CR. Okay, this 1 by CR means this is the C capacitor and this is the resistance. It is dependent on this beta network circuit. 1 by CR. Okay, this resistance is the beta network resistance, not this R1, R2. So frequencies depends on the beta network circuit, which is the we have got that if you change the beta network circuit parameters, the frequency you can change. So you can design a desired frequency wine bridge oscillator by selectively choosing this C and R. And to maintain or sustain the oscillation, to get a constant oscillation from the output, at the output, you have to put this value. R2 should be equal to twice R1. For a constant or sustained oscillation, R2 should be equal to twice R1. That means R2 equal to twice R1. That means you have to put this. Okay, so you have to put these resistances. Now these two resistances, R2, R1, are the amplifier resistances. So R2 resistance should be twice that of R1. This is called the sustained oscillation condition. Then A beta should be equal to 1. Okay, so this is the condition, two oscillation condition. For the sustained oscillation condition, you have this R2 equal to twice R1, R2 equal to twice R1. So this is the sustained oscillation condition. Then what will be the gain of the amplifier? The gain of the amplifier you can calculate, gain equal to 1 plus R2 by R1. It should be 3 because R2 by R1 equal to 2. So gain of the amplifier you have 3. Then from this condition or Bartholin condition that A beta equal to 1, you can easily calculate that beta equal to should be 1/3. So this is the condition for the sustained oscillation. That means a constant oscillation will be produced by the by the wine bridge oscillator circuit. It is if you put A equal to 3 or R2 equal to twice R1, then obviously beta should be 1/3. And the oscillation frequency is omega 0 equal to 1 by CR or F0 equal to 1 by 2 pi CR. So in this way, you can analyze any oscillator circuit and get the oscillation frequency and the sustained oscillation condition with the help of Bartholin criteria A beta equal to 1. Just you have to calculate the amplifier gain A and the beta network beta fraction. I hope that you have understood the discussion, how to analyze the circuit with the help of a particular circuit, which is called the wine bridge oscillator circuit. Have you understood this one? Is there any question? Any other? This mathematics is very simple, but I have chosen this way such that the mathematics is easy. In some books, this mathematics becomes very complicated because they have not chosen this ZS and ZP equivalent resistance and not calculated this one, then the mathematics will be very larger one. So you just follow this one, then it will be very easy to calculate the condition and the oscillation frequency. To understand also, this is very easy way. Any other question? Anything? Anyone wants to ask anything? Is everybody getting me? Okay. If you don't have any question, then today we conclude here. Okay. Several students have left. What happened today? Acha, ठीक है, okay, ठीक है. We will continue the next day because I have to finish the major part of the syllabus. So I don't have. তাই তাহলে শুক্রবার দিন আমি তাহলে 10টা থেকে রাখতে পারি, ঠিক আছে, যদি না থাকে। ঠিক আছে, ওকে। মানে I have to finish other classes or other chapters also. This is the oscillator chapter, okay? After finishing